2.6D related rates. Oh, before I get started, I need to recap some things. So first, let me bust out a triangle here. So it's a triangle, right? And let's suppose I have an angle, which I'm going to call theta, and it's this corner. Okay, if you recall from geometry, actually, let me move this over a little bit so I can have a little bit more space. If you recall from geometry, the angle tells you what side is considered the opposite and what side is considered the adjacent. So like this would be the opposite. And then the side down here next to the angle would be the adjacent. And then of course the hypotenuse is always the hypotenuse. Let's see, other things to review. Sine of the angle is the opposite over the hypotenuse. Cosine of the angle is the adjacent over the hypotenuse. And tangent is a combination of both. Tangent of the angle is the opposite over cosine. Oh, sorry. Over the adjacent, which is just cosine, right? Sine over cosine. Okay, so this is the basics, right? Sine, cosine, tangent. And so we're going to do related rates with this form of trigonometry. It's not just the Pythagorean theorem. But we're mostly going to use the following equation along with the one that I just wrote. So this one, right, we're going to use the most. And then the other one that we're going to use mostly, well, not mostly, but it's basically caused by using tangent of theta. We're going to have to derive it. And so the derivative is secant squared theta. But of course, because it's a related rate, I'm not deriving with respect to theta, which is just basically x, right? So technically, this would be dt, right? And then because I'm deriving with respect to time, and theta is obviously not time, then I'm going to have to do the implicit d theta dt. Okay, so this is basically what we're going to use. I don't think I skipped anything. All right. I mean, there are other things that might have to come up. We're not limited to this, right? I didn't write every single possibility, but there are other things that you're required to know. For example, cosine is 1 over secant, or secant is 1 over sine, right? I mean, we do have secant right here, so it might be important to know that secant is equivalent to 1 over cosine, right? Okay. Example 1. Bugs and Daffy finish their final act by dancing off the stage with a spotlight covering their every move. If they are moving off the stage along a straight path at a speed of 4 feet per second, and the spotlight is 20 feet away from this path, what rate is the spotlight rotating when they are 15 feet from the point on the path closest to the spotlight? Okay, so spotlight. Here's a spotlight. Okay, here's the light. It is located, where did it say? 20 feet away from a path where Bugs and Bunny are walking. So we're going to we're going to treat the top part as the path. Okay? So then the spotlight is located 20 feet away from it. Now, distance is always measured with a perpendicular line. So this is a right triangle. Now, Bugs and Daffy, they're walking off stage, so they're going this way. Now, they're walking off stage at a speed of 4 feet per second. So if I call this x, right, they're walking at a rate of dx dt 4 feet per second. The spotlight's 20 feet away. What else am I missing? What rate is the spotlight rotating? Okay, so basically, if they're walking away, the spotlight has to follow them. So it is rotating. We're going to call this angle theta. And so I'm wanting to know what is d theta dt. And then they want us to figure out this rate when Bugs and Daffy are 15 feet from the point on the path closest to the spotlight. So basically this right here is the point on this path that is closest to the spotlight. Perpendicular distance is always the straightest, I mean the shortest. And so basically when x is 15. Okay, so to start off, we don't know the angle. Okay, so too many variables here. I don't know d theta dt, which is what I'm trying to figure out, and I also don't know the angle. I don't know the hypotenuse, but that's not really important in this scenario because I am going to use tangent of my angle, which equals the opposite, which is this right here. This side is the opposite. I'm just going to call it x. And then the adjacent, which is this right here, which I can call y. Now, the distance of the spotlight is not moving. Therefore, this is constant. So I don't have to use y. I can just use it, 20. So this is my equation. But again, as I said before, I have two variables. That's not going to worky for me. I don't know what the angle is, and I do not know, or well, I do know what x is. My bad. What I'm not going to know is the rate of d theta, or theta, sorry, d theta dt, which is not here yet. So let me just keep walking along this path so that you can see. Okay, so derive tangent theta is secant squared theta d theta dt, and then x over 20 is just 1/20th x. If I derive that, I get 1/20th, and then I get dx dt, and you can see that x is not really important in this part of the equation. It's important, just not for here. Okay, so what I was trying to say earlier, I got all flustered. I don't know theta, but I also don't know d theta dt. So that's two things I do not know. Now, the whole problem is based on what is the rate of the spotlight moving. So d theta dt is basically what I'm trying to answer. So theta, I should be able to find it somehow. All right, so how to find the angle? Well, if we go back to geometry, it's totally doable here. I can find the angle theta. Okay, so theta, right? I can use, let's see, I have the adjacent and I have the opposite. I can use tangent. Tangent of my angle, theta, is equal to the opposite, which is 15, and the adjacent, which is 20. So here, x is important again. So tangent theta equals 15 over 20. So theta itself is equal to the tangent inverse of 15 over 20, which is 3/4. Right? I'm not going to write 15 over 20. It is 3/4. So you pop that into the calculator, and this would be a question that you would need a calculator with. There aren't any exceptions here. And you would figure out what the angle is. Now, you could figure out what the angle is decimal, or you could just use this entire thing as your angle, because we're going to plug it into the equation up there. Your choice. If you want the most accurate answer, tangent or inverse of 3/4 is going to give you the most accurate answer. Or if you don't want to plug all that in, when you find the decimal, round to as many decimal places as possible. So you normally round to 3 decimal places? Well, I'm using double. That way I can make sure that my answer is pretty accurate. There were more numbers, I'm sure. I think I recall more numbers. All right, anyway, so here is my angle. Finally, I have that, so I don't have to worry about that anymore. So secant squared of 0.6435501 of d theta dt, which is eventually what we're going to figure out, equals 1 over 20 times dx dt. Let's see, if you recall, dx dt was 4. Okay, so then d theta dt is equal to 1 over 20 times 4. Now, the 1/20th times 4 is 4 over 20, which is basically a fifth, or 0.2. And then we're going to divide the secant squared times all of that over to this side. So d theta dt equals secant squared 0.6435501. All right. Now, if you've ever looked at a calculator, there isn't really a secant button. There's only sine, cosine, and tangent. Well, just the basic calculators, right? But either way, make your life easier. Secant squared being in the denominator is a good thing because secant is the inverse of cosine. So secant is 1 over cosine, which means 1 over secant is just cosine. So that secant squared being in the denominator is a gift because simply I can just convert it to cosine, and when doing so, it's not going to be the denominator anymore. It's just going to be in part of the numerator, so it's on top now. So I can use cosine instead of secant, and I get rid of the fraction all in one. So cosine squared of 0.6435501, and now I get to multiply that in my handy dandy calculator, right? Because this is a calculator question, there is no doubt. And then I get 0.128, always to 3 decimal places. Now, the units for an angle is always in radians. Okay? If your calculator was not in radians, then your problem might be there. Oh, how about I just call rads? And then the time, I believe, was seconds? Yes, seconds. So 0.128 rads per second. This is the rate of the angle's rotation due to Bugs and Daffy walking off stage. Okay, example 2. A camera is located 50 feet from a straight road along which a car is traveling at 100 feet per second. Okay, so I'm going to make another triangle. Okay. So here's my triangle. And so there's a car traveling. The camera is located 50 feet from the straight road. So let's say that this is the road. Let me highlight. This is the road right here. And so the camera is located 50 feet from the road. So here's the camera. That's my camera, okay? So 50 feet from the road. And so then there's a car traveling. And the car is traveling at 100 feet per second. So I'm going to call this x. And then the car is traveling dx dt at 100 feet per second. Let's see what else. The camera turns so that it is pointed at the car at all times. So this camera is turning, right? Here's the angle here. Let's see what else. In radians per second, how fast is the camera turning as the car passes closest to the camera? Okay, so that last sentence tells you what direction the car is going in. Let me pick green. So, closest to the camera is here. This point is the closest, which means that the car is actually traveling in that direction. It's headed this way. So by heading towards the angle, making this side smaller, that means that my rate is actually negative. And oh yeah, and I forgot what I was thinking. The angle is rotating in this direction. Okay, so we're basically figuring out how fast the camera is turning. So we are looking for d theta dt. Now once again, I do not know what my angle is. Okay, well at least it wasn't just blatantly written in the problem. But if you think about it, um, the cameras just open up, right? But if it rotates all the way to right here, the closest point to the road, my angle, you can consider it as being 0. Okay? It's just completely 0. It has closed off because the car, that's the furthest it can go. So our angle is going to be 0. So theta is 0 degrees. That's a degree symbol, doesn't look like it. Alright. So once again, figure out what you got. I have my opposite to the angle, and I have my adjacent, which is good news because it means that we are using tangent. Tangent is opposite over adjacent. Derive, you're always going to have to use secant squared theta d theta dt equals 50. Okay, now the x. Oh, I said opposite over adjacent, didn't I? That's not what I wrote. Oy. Okay, opposite over adjacent. Let's try this again. Opposite over adjacent. Okay, if I derive that, that's just 1/50th, right? 1/50th times x. When you derive that, it's just 1/50th, right? So 1/50th and then dx dt. Okay, plug in what you got. So secant squared of theta. Okay, theta, we discussed it is 0 because this angle is just basically closing itself in order to be right on this line, which is where the car is going to be the closest to. So when it passes this line, the angle's closed. Okay, over here, it's open, but when it ends up going this way, it's closed. Right, so the angle's 0. Right. D theta dt is what we're looking for, so obviously I'm not going to have that to plug in. And then 1/50th, and then dx dt was negative 100. Okay, so let's simplify. 1/50th times 100 is, or negative 100 is negative 100 divided by 50, which is negative 2. Now, the secant squared theta, I could divide that from, to the other side. Divide it from there. And then, now, just like before, this can be converted to negative 2 times cosine squared of 0. And you should know what cosine of 0 is. Cosine at 0 degrees is the x-coordinate at 0 degrees. So the cosine of 0 is 1. So negative 2 times 1 squared, which is just 1. And so it's just negative 2. I'm going to go ahead and erase that. And the rads per second. Okay, that is how fast the angle of the camera is changing as the car is passing. Right. Next example. A camera is situated 4,000 feet from the launch pad at all times. At what rate is the rocket rising at the instant the angle of elevation? Or what instant the angle of elevation angle? Oops. Too many angles. Saddy. At the instant, the angle of elevation is pi over 6 radians, and increasing at a rate of zero point 0.6 radians per second. All right, so there's a rocket. Here's a rocket. There's a launch pad. Ooh, that's not a line. That's straight. Now, the angle of elevation, basically, looking up, right here. The rocket, or sorry, the camera, which is, we're going to assume is right here, and here, I'm going to put the rocket right here. Okay? I'm not a drawer, people. Here's my rocket. Looks like an arrow. Whatever. The camera is 4,000 feet away from the rocket. The launch pad. Whatever. Same thing. At what rate is the rocket rising? So it's going up. We're going to call this y. At what rate is it rising? So dy dt is what we're looking for. Let me get rid of this. Okay. At the instant that the angle of elevation is pi over 6. Okay, so great. Theta is pi over 6. And increasing at a rate of 0.6. So the angle is increasing at a rate of 0.6. So this is all the information we have. We have d theta dt. We have theta. Technically, this down here is x. If I decided to call the other one y, I'm always going to use the horizontal distance as x and the vertical distance as y. So x, and then we don't have y, but that's okay. And we're looking for dy dt. So again, here's my angle. This is my adjacent. And this is my opposite. So yes, we are using tangent. So tangent of theta equals the opposite, this time I wrote it in the right place, over x. Okay, now, like example, what was it? All right, as I was saying, like example 1, I think it was example 1. Yeah. The camera is situated. It's not going to be moving. So those 4,000 feet, those are constant. So we can go ahead and just take care of that right at the beginning. So y over 4,000. Okay, so derive. So you get secant squared again. Secant squared theta, d theta dt equals y. Let's see, 4,000. So basically, this is 1 over 4,000 times y. So the 4,000 and the 1 over 4,000, they stay. And the y becomes dy dt. Okay, plug in the stuff. Our angle was pi over 6. D theta dt was 0.6. Dy dt is what we're looking for. So basically, I need to get rid of that 1 over 4,000. And I'm going to do that by multiplying by the reciprocal, which is just 4,000. So let me just take care of that in this step. Multiply by 4,000, multiply by 4,000. Okay. Alright. So dy dt equals all of this. Now, we didn't get so lucky like in the previous examples. We didn't get to get rid of the secant by making it into a cosine and bringing it up to the top. But we can get rid of it by putting the cosine in the denominator spot, which is still not very difficult to do. You can get rid of the 4,000 times the 0.6 because that's just 2,400, right? So wait, so the 4,000 times the 0.6 is 2,400. And then the secant squared pi over 6, I want to make that into cosine squared pi over 6. But see, now it's in the denominator, so it's friendlier. Okay, that's if you want to. You don't have to. you could just leave it as secant squared theta, secant squared pi over 6 and figure out, okay, what does this equal? Alright, so 2400. Now, what is cosine squared of pi over 6? Now, pi over 6 is right here. Pi over 6 is 30 degrees. And at 30 degrees, let's see, we go 1, 2, 3, 1, 2, 3, and they're all being divided by 2, right? And all the top numbers are square rooted. But there's no point in square rooting the 1, right? And here are the coordinates. Oops, I didn't mean to do that. Coordinate, 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 right? Do, 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 do. I did mean to do that. That is a 2. What am I saying? Oh my god. Can't write correctly today. Okay, so the cosine is the x coordinate, so right here, squared. So this over that squared, which is just 3/4. So this is 3/4. No can do. So 2400 times the reciprocal of that. 2400 times 4 divided by 3. So 2400 times 4 is 9600 divided by 3. And that is 3200. Okay, dy dt, dy dt, dy dt, and this is 3200 feet per second. And that is the rate that the, what is it called, rocket is rising. Okay, last example. This scenario is a little hard to picture. I guess the wording, I stole it from somewhere, so it's okay. So let's see. I need a right triangle. Let me find that first. Okay. Well, actually. Okay, so there's a kite and it's flying at a height of 85 feet. It is flying horizontally at a rate of 2.7 feet per second. Okay. So it is flying horizontally at a rate of 2.7 feet per second. Alright, let's imagine where the kite is here, people, because kites don't fly straight up. So here's the kite. Okay? And it is flying at a rate that is horizontal. So this way. And this rate, we're going to call this dx dt. It is 2.7, but of course it's making this side smaller, so negative. Let's see what else. Assuming the string is taut, so basically tight. So the string, I hope you have an idea, is this right here. So assuming that it is tight, nice and taut, let's see, where was it? At what rate is the angle of elevation changing when the length of the string is 210 feet? So the string is going to be 210 feet at a certain time. They're wanting us to figure out what is the angle of elevation, right? The angle has to go up. What is the rate of the angle of elevation? So d theta dt is what we are looking for. Looking at this, I hope you can see that we currently do not have the angle. Now, let me label what I have. This is the opposite, and this is the hypotenuse. Oh boy, right? We've been using tangent, because that's normally what you have to use. And that's not quite what I have. So, it means that I am going to have to figure out what my adjacent is. The adjacent is down here. It's next to the angle. So I'm going to have to figure out x. Which I can do that. This is a right triangle. Yay for right triangles. I'm going to do that right below this picture. Get that out of the way. Well, actually, let me show you first why I know that I need it. Okay, so if we use same old tangent, tangent is opposite, right? Um, which is 85, and that's constant, right? What do you call that? The kite height, the kite's height isn't changing. What's changing is how it's moving horizontally, not vertically. So 85, that's the opposite, um, over the adjacent, and the adjacent is x, and that's what we don't know. And then when I derive this, because x is in the denominator, okay, so basically this is 85 times x to the negative 1 power. Oh, that negative 1 doesn't look like a negative 1. Okay, negative 1 power. When I derive this, x doesn't just magically go away. Okay, so secant squared theta d theta dt, that's what I'm looking for, equals, and then this becomes negative 85 times x to the negative 2 power dx dt. But I'm showing you this, but I'm just going to go ahead and write it as x squared, right? But it's in the denominator. That's how the negative works. Dx dt. Now looking at this now, I hope that you can tell, oh, we don't have the angle, and we do not know what x is, and that's a problem. All right, so going back to what I wanted to do, I want to find x. So it's a right triangle, Pythagorean theorem. X squared plus 85 squared equals 210 squared. When you do all of the math, subtract 85 squared from both sides, you get x squared equals 36,875. And then x itself is the square root of that, or more specifically 192.02864. I'm rounding to a lot of decimals because I want to make sure my answer is as accurate as possible. Okay, now I am missing the angle as well, which means I am going to have to find it. So it's not just enough to find x, I have to find the angle. I'm just going to move this to the side here. Okay, so I need to find the angle. So here's the first thing I have to find. Now the angle, let me look at the triangle. What information did I have? Because, you know, who's to say that you found x first? So, even though we did. For the angle, I had the opposite and I have the hypotenuse. Okay, well that's sine. So sine of theta is the opposite over the hypotenuse. Okay, so going back to geometry, if I want the angle itself, the angle is going to equal the inverse of sine. Oops. And then, okay, I don't know what I'm doing here. What's going on? And then 85 over 210, which again requires a calculator, and you can't and shouldn't be able to do this without one. So once plugging that into the calculator, I get 0.416718. Remember, I'm using a lot of decimal places. 5 or 6 is a good number, just to be safe. Right, so there's my angle. There's the second thing that I was missing. Yay! Alright, so now I can go right back to solving. I can plug this stuff in. So secant squared of this right here, 0.416718, d theta dt equals negative 85 over, let's see, what was x? X is this, but looky, there's a square, right? You see the square? So really, I can just go ahead and use this. 36875. Okay, and then times dx dt. Dx dt was negative 2.7. Okay, so then you would just really, like, multiply those hideous numbers right there. Um, okay, so negative 85 times negative, oh, negative times a negative makes it positive. I'm pretty sure this should be negative. Maybe I drew the triangle wrong. Oh, I'll take care of that at the end. No big deal. Okay, so 85 times the 2.7 divided by that there. Um, I do have an answer for that, and it is a horribly looking number. Okay, so it is negative or positive. Well, I'll worry about the negative last. I could have drawn the picture incorrectly. I'll just reanalyze my picture. 2237. Yeah, that's a pretty number. And then this, right, comes over here to the other side by dividing or multiplying as cosine. Okay. Um, I'm run out of space, so let me see what I can move here. Oops, that's not what I meant to do. This is what I meant to do. Okay, yay. So move that over. Alright, so multiplying that to the other side, or dividing, divide by secant squared of 0.4766718, or 4, oops, that's a 1. Boy. Secant squared of 0.416718. Okay. So basically d theta dt equals this. Figure out how to find that, or times the cosine squared of 0.416718. Anyway, plug that into the calculator and we get negative, or yeah, I knew the answer was supposed to be negative. Oops. Okay, 0.0052 rads per second. Now, as far as the negative, it's supposed to be negative. And I can tell you why. I guess I just didn't think it through when I drew my triangle. It's negative because, oh, I guess that would be a good example. Let's say that the kite started up here, right? Directly up 85 feet. It was being pushed this way, which is why I said negative. At this rate, the angle was initially this big. What's happening to the angle as the whatchamacallit goes that way? The angle's getting smaller. So the answer should have been negative. I suppose I should have been looking at this differently. So if I had looked at it like this, instead of how I drew it, the angle of elevation, right, this, is the same as the angle of depression. They're actually the same, because they're alternate interior angles. But anyway, so I would have still had 85 as my opposite, 210 as the hypotenuse. But then my kite would have been moving to the right. And to the right, it's making the side longer. Okay, so this is where I went wrong. The xdt should have been positive 2.7. I drew my triangle upside down, I suppose, because I was going off of so much by the words angle of elevation. I guess if we're elevating, you could make the triangle as I did initially, just don't make this negative. Okay, so let me fix that. So that should be positive, right? What else? Where else did I use it? That's it. If that's positive, then this is now negative, in which case negative, in which case my answer should be negative. Okay. Alright, no biggie. And that's that. Problems, you done. No practice problems, we're done.